Universiti Malaysia Kelantan, UMK, is an entrepreneurial university. We implement the government's aspiration to ensure the younger generation are not only highly educated, but also entrepreneurial. Our mission is to become the #1 entrepreneurial university in Malaysia by 2023, in ASEAN by 2026, and in Asia by 2030. This is in line with the National Entrepreneurship Policy, which aims to make Malaysia an entrepreneurial country by 2030. According to this vision, UMK ensures the whole university functions within an entrepreneurial ecosystem. This ecosystem comprises of 9 faculties, including the Language Centre, supported by institutes and centres of excellence, implemented with the discipline of innovation-based entrepreneurship. The university's upper management, together with UMK employees at all levels, are committed to realising UMK as a Malaysian public university well respected for its foundation of entrepreneurship. Implementing this ecosystem, the Universiti Malaysia Kelantan Entrepreneurship Institute, UMKEI, oversees 3 other entrepreneurship-based centres: the Centre for Entrepreneurship Development and Education, CEED, the Institute of Small and Medium Enterprises, ISME, and the Global Entrepreneurship Research and Innovation Centre, GERIC. The Faculty of Entrepreneurship and Business, spearheading this structure, has successfully developed collaborative entrepreneurial networks such as UMK Frontier Street, the Entrepreneurial Advisory Council, the Entrepreneurship Committee, and Gerak Gempo Keusahawanan. From the academic aspect, UMK offers 25 undergraduate programs and 16 postgraduate programs in the fields of business and tourism, science and technology, as well as arts and heritage. The university is constantly enhancing its teaching and learning system to ensure that the process of learning takes place creatively and innovatively through My Academic Integrated System, My ICE, massive open online courses, MOOC, and blended learning. UMK is committed to the development of first-class graduates to become the leaders of industry. Collaboration with world-class local corporate sectors, as well as a network of well-known regional educational institutions, is aimed at empowering UMK from various angles. This is evidenced by the increase in the marketability of graduates and graduates who create jobs through businesses. Research, innovation, and commercialization is another important part of UMK. Research funding and the number of innovations and commercialized products increase every year. UMK has excelled in various prestigious competitions. With the hashtag UMK for Society, UMK is also involved in various community activities. Our staff and students consistently demonstrate outstanding skills and abilities. With such a great spirit of teamwork, UMK has never looked back to emerge as a respected educational entity in the region. We at UMK believe that our presence will give a new look to the development of a valley of knowledge. Indeed, our core, entrepreneurship, will always make us, Universiti Malaysia Kelantan, relevant, unique and different.
Faculty of Science have been established in 2012. We are in one of the youngest university in Malaysia. We have a vision to become a pioneer in sustainability, environment and natural resource through entrepreneurship agenda.
Currently, Faculty of Earth Science offering 3 undergraduate programs. We also have 2 preparatory programs which managed at Faculty of Earth Science.
For Bachelor of Applied Science, Natural Resource with Honours, the focus of this program are much more on our biosphere, which means we are focusing on our plants, our animal, and also the management of our tropical forest. For another program, which is Bachelor of Applied Science, Sustainable Science with Honours, the program itself relate more on environmental element, which is we would like to sustain our environment together with the importance of economy and also social.
Always apply teaching and learning section by using technology such as by using GIS, drone, geospatial mapping technology and also modeling. Students also be taught with to integrate geoscience understanding from classroom or practical learning with geoscience data from a variety of sources creatively using the latest digital technology.
Science Preparatory Department is a new department and need to taking care and manage of 2 academic programs. Both of these programs will need to learn biology, mathematics, chemistry and also physics.
Faculty of Earth Science Museum, actually we have various dry and wet specimens such as insects, small mammals, reptiles. Besides that, we also have rocks, minerals and also fossils. So actually all those specimens being collected by our students.
To stay relevant, we have to be flexible. Besides flexible, we have to be unique. In Faculty of Earth Science, we have multidisciplinary research. Recently, we are focusing on the research on minerals and the fossil. Other than that, we use remote sensing and GIS in monitoring forests and urban planning. This research has been successfully done within our capacity of staff, supported with the grant that we received from government and other agencies.
We are optimistic to become one of the best faculty that focus on in environmental in Malaysia.
Okay, a very good day. Assalamualaikum and salam sejahtera to all of you. Welcome to the international webinar on management of rice soils for sustainable agriculture organized by Fakulti of Earth Science, Universiti Malaysia, Kelantan. So this webinar is one of our international activity in Fakulti and Universiti Malaysia Kelantan in order to enhance knowledge, sharing experience and also collaborative opportunity. So before this, we already have a few series of international webinar with international speakers from Japan, Indonesia, United Kingdom, and incoming event, we will have speakers from Turkey, Dubai, and also India. So if you are watching from Malaysia or other Southeast Asia countries, Nigeria, or the rest of the world, so not forget to click at the registration link in the comment section below and to register for the e-certificate so that we can also keep posted on the future event as well. Okay, we get back to the topic of webinar today. Management of rice soil for sustainable agriculture. We eat rice every day, right? So rice is a crucial part in the everyday Malaysian diet. In 1998, Malaysia produced 1.94 million metric ton of rice. So even with this high production, Malaysia still only produce 80% and need to support itself and must import from the rest. So the average Malaysian citizen consume about 82 kilogram rice per year. So basically, this is why we are here today. So gather virtually to listen and learn about management of rice soil for sustainable agriculture from our experts. So before the talk begins, allow us to introduce the speakers. our first speaker. He is lecturer of Micheal Okpara, University of Agriculture, Umudike, Abia States, Nigeria. So he is from Nigeria. It's been 7 hours with us. His research background in spatial data analysis relates to digital soil mapping and crop modeling. He specialized in quantifying the constraint to crop production and use of remotely sensed data to assess the production constraints. So he is have conducted the World Bank project before and also consult with the project for the agriculture coordination and under the Federal Ministry of Agriculture and Rural Development, Abuja, Nigeria. So now, please welcome Dr. Ezekiel Okonkwo. He is my best friend during our PhD in the Kingdom Country University. Okay, let me see.
Yeah.
Dr. Easy is already on the screen. Hi, Easy. So
Hi,
the popular
Amal.
name, we call him Easy. Okay.
Okay.
Okay, hope you are fine.
Yeah, I'm good. I'm good, Amal. Thank you.
Okay, so now, without further ado, I would like to welcome Dr. Easy to deliver his talk on mapping of soil constraint to rice production at regional or national scale. So, all right, Easy, the floor is yours.
Thank you. Thank you. Okay, I hope you are seeing my screen. You can see my screen?
Yes, you can see right now.
Hello,
Yes. And
okay.
yes, clearly, just click at the height under the screen. Yes, okay. Easy, sorry. If you can start again. Not clear. Okay, you can unmute. If you can unmute unmuted your voice. Okay. Okay, I can hear you right now.
Yeah, okay, very good.
Okay, share your screen.
It's okay.
Okay, you can share your screen.
Okay. It's already shared. Let me just put it in.
Okay. All right.
All right.
Okay.
Is that fine now?
Yes, fine.
Okay.
Great.
Yeah. Thank you.
Sorry, easy to interrupt. Sorry, easy to interrupt. Easy, I can't hear you again. I can't hear you again. Hello? Yeah. Maybe we can do slideshow. It's fine if you just leave it without the slideshow.
Okay.
Just if we can click again at the slide.
Okay.
Yeah. So we can start from here maybe, from the first slide.
Okay.
So no need to do the slideshow, and I hope that audience could see clearly.
Is that okay?
Okay, that's fine.
Okay. I said my.
It's muted. It's muted. Okay.
Let me cross check what is happening, please.
Okay.
Share screen.
It's okay. Maybe just.
If it happens again, then there may be some settings. Can you hear me now?
Yes. Yes. Clear.
Okay. Okay. Yeah. I'm here to. My name is Dr. Ezekiel Okonkwo. I'm here to discuss mapping soil constraints to rice production at regional, national scales. Rice is one of the important staple crop of the world. And the population growth means more demand for food. And as we're demanding food, we're looking for those staple food that can help us cushion the food insecurity. And we need to increase production by 70% by 2050 for us to be able to feed the growing population. But the concern here is that yields of some major crops have slowed due to several biotic and abiotic factors. And identifying those factors and assessing them are always limited by high resolution spatial information. So in this work, we try to provide useful approaches to help tackle these challenges. But our concern is that in most parts of the world, particularly in Asia, the production is high. Of over 600,000 million tons of rice are produced in Asia annually. But the concern here is that the yield per hectare is very low compared to the production size. And you can see that most continents like Oceania, which are small in population and have small rice production areas, have highest yield per hectare. And that's a big concern. Now, in order to know what is the problem or why are we having a low term in yield compared to the production size, we have to analyze the factors contributing to such. Now, in doing so, we have a designed research methodology that will help us achieve that. And our research area, we took one of the Asian countries, which is India, and in Punjab of India, where there has the highest production of rice, we use that as our study area to ascertain what are the problems, what are the factors contributing to this low yield despite the production areas. So in this research, we'll first try to generate the soil property maps as our objective, used for digital soil assessment and assess soil constraints in the production in the study area. We estimate rice yield using high resolution MODIS derived water data and compare with potential yield from interpolated and ground-based water station data. Finally, we will estimate rice yield gap and assess the factors contributing to such gap. In digitally assessing the soil constraints of the area, we first of all predict the identified constraints in the area, which are the pH for alkalinity and electrical conductivity, which is ECE, represented by ECE. The saturated electrical conductivity extract and the pH will give us information about the soil salinity and alkalinity of the area, which are the most major factors that are contributing to the soil constraint in the region. But for us to achieve that, it is always difficult to map the soil constraints. It's difficult to map soil functions. But we try to develop a method where we can now integrate the digital soil mapping we got from our initial research into the digital soil assessment to assess the soil constraint. You know, we are used to digital soil mapping where we can predict the soil properties. But in terms of digital soil assessment, few studies have gone into that because most of of the constraints we have are not in a single soil property. Some of them are in soil functions. And for us to determine that, we'll have to find a way of determining those soil functions that always contribute to the low yield we have in the region. But due to the legacy soil data we got from the region, which is not up to the number we required, we have to apply Monte Carlo simulation, MC, to estimate the prediction of uncertainties. And why do we do that? We do that because some research have said that only predicting the constraint may not give you the desired result. It may not give you the actual constraint in the region. But when it is incorporated with the prediction uncertainty, which most time people use Monte Carlo simulation, Monte Carlo simulation is an uncertainty, is a prediction uncertainty we use to ascertain the uncertainty of the accuracy of our prediction. So we incorporate this prediction uncertainty to produce a more reliable digital soil assessment. You can see the graph where we have the predicted electrical conductivity, saturated electrical conductivity extract. And you find out that the concentration is between the 0 to 4 DSMQ. That this Siemens per meter, that's the unit of signifying the ECE. And the pH are concentrated between 8.0 and 8.5. So it has shown us that these are the range of the soil property in the region. Now we can see the soil property maps. And what we are trying to show in the map above is that when you did the prediction we did without the uncertainties, gave us this map, the first map, and you can see that there are a lot of constraints in that map. We can see there are a lot of constraints as represented by the colors seen in the legend. We have those that are probably saline are being represented by yellow. The ones that are likely are being represented by red. But when we incorporate the prediction uncertainty using Monte Carlo simulation, we're able to see that the constraints of the region reduced. The salinity and alkalinity constraint of the region were lowered because we were able to present a threshold, because research has shown that when the ECE is greater than 4 DSM, that is to show that the soil is saline. But in a lower rice, where we cultivate rice, the threshold differs. That's why we raised it to 8.0 DSM. But same applies to alkalinity. The soil as alkaline when the pH is greater than 7.3. But in a rolling rice, that meaning when I mean rolling rice, a place we normally cultivate our rice, it becomes the alkalinity of the soil starts affecting the rice when the pH is greater than 8.3. So when we place these thresholds, we find out that the constraints of the region were greatly reduced. And that's what we're trying to achieve, to know exactly what are the constraint level of this place and how it affects the rice production. And when we get down to the tables, you find out that those that are likely saline about 43% of the size of the area. And when you allow the prediction uncertainty, it gets lower to almost 19%. Same applies to alkalinity. Now, in our findings, we find that using criteria more appropriate with lowland rice, areas predicted to be affected by salinity or alkalinity were far smaller than the one we used using fertility capability classification of Sanchez. You know, Sanchez is one of the greatest soil scientists that developed methods of determining the capability of the soils. And most research, for you to be able to determine the capability of the soil in terms of its salinity or in terms of its production, use Sanchez. But in this research, we apply Sanchez to determine the threshold and apply the multicolor simulation. We're able to determine the exact salinity and alkalinity of the soil. So using that criteria appropriate for donor help us to know the exact salinity and parameter of the soil. So now that it didn't end there, if we have known the salinity, the level of salinity and alkalinity of the rice soils, so what it now takes us to know, how do we now know whether there's a yield gap? Because the bottom line of our research is, why are we having this low yield of rice in the region? And we started with checking the soil functionalities, the constraints of the soil. We're able to achieve that, but how do we relate it to the rice production areas? Or how do we relate it to the potential yield of the rice and the actual yield of rice to know exactly whether this thing contributes to rice low yield in the region? And for us to do that, we have to model the rice yield. You know, most research are focused on modeling, but in this modeling, we now notice that the actual yield of rice, the one we get from the districts, most times is not the real yield, because it is the summed yield from the district. It does not necessarily give us the actual yield from the farmer's field. Then if we check about the interpolated yield, the one that they predict using information from weather station data, it still gives uncertainty, because the information they are using from weather station is from a point base, and our field may be far from the rice. Our prediction may be far from the rice field where the actual information are required. So that takes us to using a high resolution remote sense weather data to model the rice, so that we're able to get information from the pixels of each rice field. And in doing that, we looked at MODIS. We retrieved the daily minimum and maximum temperature from 1 kilometer MODIS land surface temperature. That will give us, that will cover the area of study, and we're able to give us information at pixel by pixel, by field of the farmers. We did that, and we're able to get information from the power data, prediction of worldwide data, environmental data, that give us information on weather variables. Then we incorporate that land surface temperature into those power weather variables. Then we got information from weather station of the area. But you know that most weather stations, they are limited and very dispersed. So the information from the weather data from MODIS LST and from interpolated data give us information about the prediction of that area. When we use those information, we predicted the potential yield of rice in that region, and the result shows various results. Now, in analyzing the results of the modeled yield from MODIS land surface temperature, from interpolated weather data, and from weather station data, with the one we got from the location, we found out that MODIS stimulated higher potential yields than station or power data. And research has shown that we can use MODIS, land surface temperature, for modeling, because the minimum temperature we found from our correlation, the minimum temperature from MODIS correlates properly with the station weather data. So that shows that our research is on the line. Then from the result of the prediction, we're able to find out that MODIS data simulated rice growth and yield were strongly influenced by minimum temperature. That's what I've just mentioned. And minimum temperature of MODIS data were lower than weather station or power data. But what is the outcome? The outcome is that we can confidently say that we can use MODIS land surface temperature in modeling potential use of crops. Now, when we did that, what we're able to achieve is that we got the potential use of rice from MODIS. We already gotten the potential yield we modeled from the station data. Now, it is now for us to know the yield gap. And yield gap says potential yield, the difference between potential yield and weather station data gives you the yield gap. That is from the actual and the estimated. The actual here is the yield we got from the farmer's field. So the yield we got from the farmer's field and the yield we got from modeling, the difference gives us the yield gap. And that's brought us to the yield gap analysis. But for us to do that, we now have to say, having gotten the yield gap, we now use the rice information of that region and integrate the soil constraints we got to know whether those soil constraints were mapped from at the beginning has any contribution to the gap we got. And using ANOVA, analysis of variance, from statistical software, we're able to have an interaction between those variables, the soil constraints we have mapped, and other variables, such as the water, organic carbon, and pH. Then, from our findings, we have found that the yield gap was large and stable across years and districts. The yield gap we got that area was large and stable across years and districts. Soil constraint contributed 4.8%, but the areas with that highest concentration did not necessarily have the highest yield gap. So what is trying to explain here that initially we felt that those areas we saw the high concentration of salinity or alkalinity will give us the highest yield gap, but it wasn't so. Soil constraint contributed 4.8%, but the areas with the highest concentration did not necessarily have the highest yield gap. Providing better access to irrigation water will help improve the yield by 7.7%, because we know that those areas are monsoon, and the water supply or source of that area, most of them depend on the monsoon period. And once that didn't occur on time, it affects the yield. That's one of our other constraints we found. Then specifying appropriate crop planting dates influence the variability of potential yield estimates. You know, most of them, you need to specify the actual time you plant your rice, because if you don't plant well, it affects the yield, because they are dependent on the water from the monsoon period. So in all, soil constraints contributed to the yield gap, but not to a larger extent. And we're able to develop a method of predicting the soil functions, which are the soil salinity and alkalinity, which are always difficult to assess. And this research has shown us that land surface MODIS temperature can be used to model potential yield of rice, and it gives us a larger coverage of the area we're working on, unlike the station weather data that are point-based. So, ladies and gentlemen, this research has given us an idea of what we're going to do to help improve the rice production and other crops in the region and most of the globe. So, in conclusion, we now found out that incorporating uncertainty in soil property estimates improves digital soil assessment. And that flexibility of the digital soil assessment approach to appropriately define soil constraints that models the rise surface temperature has clear advantages for use in crop modeling. And use of digital soil mapping techniques with high resolution spatial data to assess yield gap explain 26.3% of the yield gap of the area. The contribution of soil salinity and alkalinity to yield gap was not evidently seen because flooding diminishes the severity, as we always know in low-rise rice. Thank you for listening.
Okay, thank you very much, Dr. Easy. Okay, this is a very interesting presentation and also awesome finding, I think, and the informative sharing knowledge in mapping the constraint, your technology, MODIS and the SM, it could be used by the other researchers, planners and decision maker, I think, to provide sustainable agriculture. So Dr. Easy, if you don't mind, for the participant, if you can drop the comment on the comment room, comment section, in order to ask for the panel. And how about if we collect all the questions until the end after the second speaker? Are you okay with that? Are you okay with that?
Yeah, it's fine, it's fine.
Yeah. Okay, thank you very much, Dr. Easy.
It's okay.
Yeah. Okay, so we now move to the second speaker. Our internet speaker is our very own alumni who graduated in 2013 with a Bachelor in Applied Science Natural Resources. So from University Malaysia Kelantan. The awesome, energetic and cheerful youngest brothers in faculty, okay, through the UMK Young Lecturer Scheme, he's pursue his PhD in soil nutrition from the University of Aberdeen, UK. His work include using the stable isotope to study how plant influence the potent nitrous oxide gas from rice and tropical forest soils. So in 2019, he was appointed as a senior lecturer at the Fakulti of Sains UMK and now the coordinator of the UMK Science Foundation Program. So now please welcome Dr. Muhamad Firdaus Karim.
Hello, hi, Assalamualaikum.
Yeah, kesalam. His popular name, Dr. Ferd. Okay, Dr. Ferd. Are you ready, Dr. Ferd?
Yeah, I'm happy to
Okay.
go.
Okay, you will present the topic on is it carbon derived from plants or soil organic matter that drive the nitrification in rice cultivars? Okay, all right, Dr. Ferd, the floor is yours.
Thank you very much to Dr. Amal Najihah, our moderator for today. I'm actually very honored to be here, to be invited as part of the speaker representing the Faculty of Earth Science, Universiti Malaysia Kelantan. Well, as for today, I find it very interesting when the first speaker spoke about how you can actually use a model to predict the soil constraints. Because that ties in really well to what I'll be talking today under the theme on rice and also nitrous oxide emissions and reduction. And specifically today, I'll be talking to you guys about is it the carbon that is derived from plants or soil organic matter that could actually drive denitrification in rice cultivars. Now, denitrification is one of the key pathway, where N2O, and N2 is being emitted. So this project was undertaken by me when I was doing my PhD, together with my two supervisors, names on the slide, Professor Liz Baggs from University of Edinburgh and Dr. Nicholas J. Morley from University of East Anglia, so back in 2014. All right, so let's go, peeps. I hope this will be interesting for you guys to listen to. All right. Okay, now rice, as our first speaker mentioned just now, Oryza sativa, or the Asian rice, is our staple food, globally. it is most widely consumed, yeah, by 1/2 of the global population. There's 2 subspecies, Japonica, right? So the short grain version, and also Indica, the long grain version. If you look at the figure that I present over here, the production of the rice, yeah. So the top 10 countries, yeah. So on the top list is actually China, yeah. And then you have India, Indonesia, Bangladesh, Vietnam, Thailand, Myanmar, Philippines, Japan, and Brazil. And I did check, yeah, the rank. Malaysia do rank in the top 100 of one of the producers. So it is one of the crucial, yeah, or the significant crop. All right. So if you look at the production share of rice, yeah, in Asia it's 90.6%. Yeah, it's one of the largest. And if you look at the production yield or quantities of rice, yeah, globally, you can see the graph. You know, it goes up. Yeah. So the red lines represent the world production of rice in million tons, and then the blue lines indicates the world area harvested. Yeah, so the area that we utilize to actually cultivate rice. You can see latest in 2018. This is a fact by the FAO. We have 755 million tons, yeah, of rice being produced at the area of approximately 162 million land areas being utilized to cultivate rice production. Now, yeah, we do admit, yeah, we do agree that rice is very important, it's very significant. And if you can have a look over here, rice cultivation, it has added 11% of the potent N2O gas to global agricultural N2O emissions. Yeah, and yeah, so the main reason, you know, the key reason over here is because there's increasing demand for rice and wide application of synthetic nitrogen fertilizer use. Yeah, through and then if you can have a look at the figure that I show as well, the graph, so the graph over here clearly, yeah, back in 1970 all the way to 2010, from the IPCC working group reports, you can see that there's an increase in the N2O gas emissions. So the one in this blue, yeah, slightly dark blue over here, we call it ocean blue perhaps, yeah, all the way until 2010. Yeah, so yeah, why nitrous oxide? Yeah. So N2O, okay, it is commonly known as the laughing gas. Yeah, it has a very high global warming potential. It is actually 300 times more effective as compared to the CO2 gas. And then its global lifetime is approximately 114 years. That means it could stay up there for approximately 114 years. And also the free radicals of it, which is nitric oxide, NO, yeah, it catalyzes the breakdown of the ozone layer. So that causes the thinning of the ozone. And then one of the significant causes of the N2O emissions over here is the intensification of agriculture and the use of synthetic fertilizer, as I have indicated in earlier slides. And 80% of these N2O emissions come from agriculture. We cannot avoid this, yeah, because there's increasing global population and clearly there's increasing food demand. Yeah, so the only way that we can go is to find what's the most sustainable way, yeah, that we could cultivate the crops and at the same time we could help to lower the emissions of the N2O gas. So and that leads to, so just perhaps a little bit more on N2O, yeah? So the source of N2O itself. If you look at this, yeah, this is a very common diagram that if you go on Wikipedia, you could have a look at this, all right? It's the nitrogen cycle, yeah? And this is an illustration that I did to actually highlight, yeah, the how nitrogen move about, yeah? So between the atmosphere and the soil, okay, the input of the nitrogen, yeah, it can be inputted through the deposition process or by application of the fertilizer, yeah, incorporated into organic matter, and then it could mineralize into the soil mineral and pool where this, yeah, so you have caps where the N2O gas could be emitted, yeah, and also N2, yeah, and also NO. Yep. And N can also be taken up, through plant uptake, and also microbial immobilization, where N is being stored for temporarily in the soil microbes. So what I'm interested to look at, because the title today that I've highlighted is denitrification. Denitrification is one of the gaseous and loss pathway where nitrate is actually reduced into N2. But before that, okay, so we know what are the issues, we know what's the problem. So we want to know like what has been done. All right. So currently the mitigation strategies is to actually improve the fertilizer nitrogen use and the soil conditions. I'm pretty sure most of you are familiar with the 4R principles of nutrient stewardship. Yeah, so it's the right source, the right rate, right time, and the right place. And from Bob Bree's article, I think he has actually summarized a few more strategies that includes reducing the nitrogen application rate, accounting for the manure and slurry, using inhibitors, and then you split the nitrogen application, and also you cultivate high nitrogen use efficiency crop. Now this is interesting because this relates with my work over here. So here's the thing, you look at the background, you could clearly see it's a picture of the rice plant. So we are interested to know how do plants influence the production of N2O, and how it can be further reduced to dinitrogen N2, which is a harmless gas. And then the key questions that we want to know, is it the carbon that is derived from the plant? Carbon derived from the plant could be from the root exudates of the plant, or from the dead decaying root parts of the plants, or is it from the soil organic matter that actually fuels the denitrifications? All right. So CO2 can be fixed by plant and can be transferred into below ground into the soil, and you can see it is very crucial, all right, to fuel the nitrate reduction process over here. All right, and so previously, what people have demonstrated that with the further it goes in the pathway, all right, from nitrate to nitrite to nitric oxide to N2O and N2 seems to be depleting. So there seems to be a carbon depleting situation in the soil, and that affects the soil carbon stocks. And mostly this could be the reason where N2O is being emitted more. So we designed a model glasshouse experiment, all right, because we want to perhaps control a few parameters, and here's the experimental design. So we use two soil with two varying organic matter content, or the percentage. Okay, so within one is high, 11.3%, and the other one is low. And then we use two different rice cultivars. All right, so this is Bridan 28 and BJ1 is a cultivar. From, if I'm not mistaken, it's from Bangladesh. All right, the Rice Research Institute, IRRI, and this is from Adam Price Rice Research Group in Aberdeen. All right, you could clearly see. For the differences between these two cultivars are, for Bridan 28 is a fast-growing species. It's a lot. So the root is not as deep-rooted or spread-rooted. It's actually shallow rooting as compared to the BJ1 cultivar. So, and we also use this. And all right, so in order to detect or to look at the how carbon that is derived from plant influence denitrification, we use carbon-13 stable isotopes. All right, so we pulse label the carbon-13 gas onto the rice plants. So the rice plants will take it up. All right, will assimilate the carbon-13, and then we apply the nitrogen-15 fertilizer, potassium nitrate, at 20 atom% at 3 splits applications. All right, because we want to see, all right, at different growth stage, at different growth stages, what happened to the hold on for a second. I think I lost my camera for a bit. All right. Yeah, here you go. I'm back. Sorry. Oh, you went there again. I guess I'll continue without my camera for a bit, yeah? If that's okay?
Yes, okay.
All right,
Yes,
okay.
that's okay.
All right, and then so we apply the fertilizer here, and then we label the plants with carbon-13, and then we do the gas sampling across 3 growth stages. And let's have a look at the result. So for researchers who work on greenhouse gases, yeah, so the flux is the most interesting part. Yeah, you could clearly see after we apply the potassium nitrate fertilizer and we pass label, you could see a peak. Yeah, a peak to show that there is emissions of the N2O at the early part. But what's interesting is how long would this peak actually sustain or remain, yeah, as compared to the pots that we do not have any plant on it, right? Unplanted pots. So here's the N2O emissions, and here's the CO2 emissions, and here are the isotopes gases, yeah, for 15N2O. It shows the similar trend. And then for 15N2, the dinitrogen, yeah, the harmless gas, and the 13CO2. So this indicates that it's the CO2, yeah, that's been emitted, and most probably, all right, it's from it's actually derived from the rice plants. So I know it's a bit complex looking at these diagrams, but I've actually simplified it a little bit over here. So the idea is when you see a peak, all right, you see a positive plant effect on the emissions. And if you do not see a peak, all right, so it's a flat line, which means there's no effect, which is actually similar with the pots, there is no plant. And if you see a negative peak, it shows a negative plant effect on the emissions. And then you could clearly see from this diagram, yeah, during the flowering or the grain filling stage. All right, okay. So let's go one by one. All right. So at this at the early stage, active vegetative stage in the high organic matter soil, yeah, where there is more organic carbon and organic nitrogen in the soil, you could see a positive plant effect for Bredon 28. Yeah, it's the cultivar with the shallow rooting system, yeah, and then as compared to the lower organic matter soil, clearly you see a negative plant effect. So the emissions were like very low, which means at this stage, when there's more organic carbon and nitrogen in the soil, the plants couldn't capture it, and so more is leaked. Yeah, more is being emitted into the atmosphere. All right, so a quick overview on that. And then we also measure the nitrogen use efficiency. All right, this is to indicate like how much. So we apply the plant. We apply the fertilizer to the soil, and then we look at how much nitrogen can the plant utilize or uptake. All right, so and that is being so we estimated that using the nitrogen use efficiency formula. All right, so the plant 15N, that is derived from the fertilizer we applied, divided by the fertilizer and applied milligrams of nitrogen per pot, then we times 100% to look at the percentage. And what we get, if you look at this figure over here, what's really interesting, during the flowering and grain filling stage, all right, you could see, like a big increase in the nitrogen use efficiency for Bredon 28. Now that's a fast growing species, and you can clearly see over here there is some allocations of the nitrogen. Well, if you look at it logically speaking at the stage, all right, is the grain filling stage. So the plants need more nitrogen, all right, to grain fill. Okay. So, and later on for BJ21, it's during the third stage is when we could see, there is more nitrogen use efficiency because they only started grain filling at the later stage as compared to Bredon 28. Now, so that is in terms two aspects just now. I've presented to you guys in terms of the flux, you get a higher N2O emissions when the plants are a lot smaller during the active vegetative stage in a higher organic matter content soil as compared to the lower organic matter content soil. And then I've shown to you guys that during the second growth stage, is when you see there is a higher nitrogen use efficiency. Also not presented in the slide today is we also look at the relationship between the carbon dioxide emissions, so the CO2 emissions and the N2O emissions using correlation analysis. And from the analysis, it shows that the role of carbon that is derived from plant, is more significant during the second stage, that is the flowering and the grain filling stage over here. All right, as compared to the later stage. And the role of carbon in fueling further reduction of N2O to N2 becomes more significant and important during the maturity stage, when the plants are a lot more mature and stable and they are more efficient in utilizing the nutrients. All right, so this is a summary, all right? It's an illustration of two scenarios. One in the planted soil, all right? So how the presence of plant, through the plant roots could actually add on to the soil, how they moderate, how they utilize the soil covering pool, and that actually affects the denitrification process or the nitrate reducing pathways. All right, low nitrate availability due to plant and microbial end demand. All right, but there's high carbon pool with plant derived carbon fixed from a larger plant, so it becomes a very highly reducing condition. So therefore, it could enhance further reduction of N2O to N2. Now remember again, N2O is a harmless gas as compared to N2O, the potent greenhouse gas. Our aim is to find out whether it is possible to actually fuel or reduce the emissions of the N2O and increase the DB production of N2 rate, all right, as compared to the unplanted soil. All right, so when there is no plants over here, there's high nitrate availability, right? There is no plant demand over here. There's no plant to actually take up the nitrogen. So there's no plant derived carbon that exists, only soil carbon that is from organic matter in the soil. So this would actually expedite or increase the N2O emissions. All right, so and here's a very interesting diagram that I usually do this. All right, I usually map so the whole idea how what is the bigger picture? What's the overall view of the science behind it? When we compare the two rice cultivars, all right, slow growing and fast growing, all right. So both have their own strengths and advantages, but we look at the plants that are slow growing. It tends to be less leaky in terms of releasing N2O because its ability to capture and retain more to capture and uptake more N could lower the N2O emissions. But the fast growing plants also has the potential to do so, all right? Because during the later stage of the experiment, when the plants are very mature, you could clearly see that there is a strong relationship between carbon that is derived from the plant and the production of N2 at the later stage. So it's very tricky, So what's the take-home message for the audience who's watching online? So do plants have a significant influence on N2O emissions and reductions to N2? Yes, definitely. How? All right, it's the power of the carbon to fuel denitrification. There is N2 to N2, and we know that at different growth, with different growth strategies, it could actually influence the carbon stock, in the soil. Also the nutrient uptake efficiency, resource allocations, and the root rates. So know your rice cultivars, all right, and know when exactly to apply the fertilizer in order to lower the potent N2O gas emissions to the environment. And that is the approach towards a sustainable agriculture. So, yep, I would just like to say thank you to everyone who's involved in this project, and of course to University Malaysia Kelantan, who actually fund my PhD and has given me the opportunity to experience and learn and come back to contribute, and of course to all the members as written on the slide. And that's it from me. Thank you.
Okay, thank you very much, Dr. Ferd. It's very awesome and interesting finding I can see how the carbon and 2O and also N2 is influence from the plant, rice plant. What catch my eye is the drawing. Is it you draw yourself?
Yes.
Wow. So you're
Yeah.
very talented in drawing because it's very cute. You see it before it's growing and maturity, and so you draw it leaf by leaf. Huh?
Well, okay, so the rice plants is not my own drawing. I think it's available on the textbooks, but all the other like illustrations to support the process is from me, because I thought it's a bit, at times it could get very tough to understand, you know, like a simple process. And when you draw them and illustrate them, it's a lot easier for you to process. So, yeah.
Yes, agree. Yes. Okay, thank you very much. All right, to all the viewers who are watching right now, so we come to the question and answer session. Okay, before that, don't forget to also to mention your name. Okay, Izzy, can we call you back for the question and answer session? Yes. Thank you for waiting. Okay, now there are a few questions here. Let me pick one. Okay, from Rahmat Shazi. Okay, Rahmat Shazi. The question is, this is for easy. Okay, we have seen big variances in rice crop yield in field in Burnham Valley that are next to each other. So based on your experience, what is the highest spatial resolution the MODIS data is usable at keeping all soil constraint data constant? Okay, that Burnham Valley is in area of Selangor. Yeah.
Okay. To Rahmat, your question. Thank you for your question. From my experience in research, based on my research, the MODIS data, if you are looking at, MODIS has a different variants. If it is for the land surface temperature, which we used in modeling the potential yield, the highest resolution you can get, from my knowledge as at now, is 1 kilometer. 1 kilometer resolution. That is we can call it the highest resolution. Yes, when we talk of highest, it means lower in remote sensing. So it is 1 kilometer resolution you can get from land surface. But when you are talking of vegetative data or MODIS vegetation data, you can get 250 meter resolution. But for the purpose of this research, that will help us to model the potential yield of rice, the highest we can get is 1 kilometer resolution. And it can help you to generate those land surface temperature you can incorporate in the model to predict the potential yield. That will help you now have the difference between the potential yield and actual yield to know the yield gap. So that is my recommendation for now. And that is what is obtainable anywhere in the world. Thank you.
Okay, thank you very much, Izzy, for the very clear explanation and answer. Okay, next question. We still have one more question for Dr. Izzy. Okay, if possible, it is from Hizami Hassin. If possible, may I have your enlightenment about how difficult to predict the uncertainty in your study?
Okay. Hassan, it is very difficult, I may confess. It's difficult, but it's not something you cannot do. Uncertainty, that's why most researchers, after the main research, will not involve themselves in the uncertainty aspect of the research. Uncertainty determination brings about the accuracy of your prediction. But because of the difficulty in predicting the uncertainty, most researchers will just end up at the result without confirming the uncertainty. But in this aspect of our research, there are two difficult things involved here. Is that we are not only predicting the soil properties, after predicting the soil properties, we try to classify the soil functions, which are the salinity and alkalinity, which you cannot just predict as a soil property. Now, in doing that, for us to ascertain the accuracy of our prediction, and based on the fact that we had a limited data for our prediction, we now have to involve the uncertainty. And you know that the stochastic simulation of spatial distributed properties is always a difficult thing. But if you involve Monte Carlo simulation, Monte Carlo is a person that propagated the stochastic simulation of spatial distributed data. And Monte Carlo did a good job that will make this very simple for you. It is just about the realization of trying to give a propagation of the data you have and introduce. You know that one thing we should be clear of is that in digital soil mapping, errors occur at various stages or various processes of the prediction. So, and those errors will now accumulate to the map at the final stage, which is the map. You know, there are stages of digital soil mapping. So each process you are doing, there are some errors that are involved, both the data, the cleaning of the data, the prediction, all those things, fitting of it in the model, all those things has errors. But what happens is that the whole errors will now accumulate to the final stage, which is the map. Now, in order to solve that problem, you have to use Monte Carlo simulation method. Monte Carlo, what does it do? Monte Carlo always try to help us by simulating the considered, and we track those errors from beginning to the final map and be able to give you a final result without much uncertainty. That's what Monte Carlo does. So it begins from the process of the beginning. That's why it has to do with realization of the variables from the beginning. Much demonstration may not be there because most of these things you need to, for the person to understand it properly, you need to write some things on the board, on the screen, for the person to understand. Because I involve a lot of mathematics. There are a lot of mathematics that will involve, equations are involved for you to, but the summary is that you can do it when you involve some of these stochastic simulation like Monte Carlo. And what Monte Carlo will do is that it will help you to track those errors from the beginning of the process of your digital soil mapping till the final map or the final result is produced. I hope this answers your question.
Yes, it's very clear to answer the question. Okay, thank you very much, Dr. Izzy, for a very clear answer. And now I think this question is to Dr. Ferd. Okay, it's also from Hizami Hassin, I think. Okay, how's your opinion about the rice cultivation in Malaysia in terms of their production? And how about the nutrient content in rice compared to the neighbors' production, which is Thailand? If you have any finding, yes. Question from.
Thank you very much, Mr. Hizami Hassan. He seemed to be a very, engaged in this webinar. All right, that's a tricky question. That's a tough question for me to answer actually, because my work is actually very limited to the scope of the rice cultivars that I use from Bangladesh. But I mean, I do have some context and a quick conversation with a few friends who has worked in UPM. Where we do have our own rice cultivars varieties, and it's actually up to plant breeding technology, where if we could design plants, if we could design rice cultivars that are highly adaptive in our environment in Malaysia, so that could utilize NPK, like use nutrients very efficiently, adopting this sustainable approach, alternating wetting and drying, and also to lower the greenhouse gas, that would be great, But if you're talking about the quality of the rice that we get, so it goes down to the cultivars that we use, So I don't really know much yet, but I'm interested to look further, and hopefully if there's anyone from UPM who's listening, do reach out, or like I've written down my email, so probably we can work more along that line. Okay.
Okay. Yeah, this is a new question coming out. One question from to Dr. Ferd. Okay. It's from Rohazaini. Is climate change has impact on rice production quality? And if yes, what will it be?
Whew, wow. Yeah. Yes. So with the change of climate, so there is a change of the pattern of rainfall. It affects the yield. It affects our rice production activity, of course. And with the increasing CO2, the carbon dioxide emissions into the atmosphere, it could impact actually the N2O emissions. It could have a impounding impact on the nitrogen cycling, because it could disrupt the carbon balance. More carbons that we have in the soil is now in the air, so it would affect. So that's for sure. I hope that answers your questions.
Yes, yes. I think it's already answered the question. Okay. Last but not least, have one more question to Dr. Ferd also. Okay. How about the oil palm? Is it the influence of nitrogen and carbon is the same? This is from Azhar Abbas. Yeah.
Okay, so this is actually very interesting, because a few of my friends who are in Aberdeen, now in SPOB and MPOB, so they did their work looking at N2O emissions from the oil palm plantations. And one of them, I think she's here and she's listening, Dr. Liana Zain. She works on the biochar applications on N2O emissions. So the concept or the fundamental is still there. So we all look at how carbon influence N2O emissions. So hers is actually looking at how addition of the biochar could actually N2O emissions. In some sites that she did, yes, the data show that it's actually significant. It has the potential. In some research, they add crop residues to soil to add more carbon into the soil. And in my research, I look at the just the potential on the plant itself against the organic matter carbon in soil. So it's more or less the same in that context, but I'm not entirely sure in terms of the magnitude, because I don't work in the oil palm industry, so I don't know how much N is being applied and how much we're able to lower and reduce to N2. So that will be interesting to have Dr. Liana Zain perhaps next time to share with us.
Okay, great. Okay, thank you very much, Dr. Ferd, and also Dr. Easy. Last but not least, I think the question from me, do you think, first of all, to Easy, do you think both of you can collaborate? Yes, it's the same for rice soil, but a different angle. Do you think it can collaborate for mapping of nitrogen and carbon? Is it possible, Easy?
Very interesting.
It's I think research is collaborative, and from Dr. Ferd's finding is very interesting, and we can cooperate there, trying to find out using the remote sensing and digital soil mapping aspect. It will help now to know what are the carbon content of the soil, and from most times the own research goes to the lab, get the soil from the field, go to the lab, get the results. Now, what are the impacts of those results? And most times, why we are involving digital soil mapping, most of these aspect of research is that when you go to the field, based on funding and manpower, there's a limited number of places you can cover. But with digital soil mapping, I can cover the whole of Malaysia in my desk with information, maybe scarce information from the field. But doing that using manpower, the funding will be high and you will involve much people. So our work reduces the tediousness of your work and giving the accuracy of what is happening now. You know, you can only get information from the soil. I will get information from the soil, get from the satellite, and combine to get more solid and the more trustworthy results. So it's a good collaboration if we to continue from here. And just like the question they asked Dr. Fine, somebody asked about the impact of rice, what climate change has an impact of rice. You know, during my research, I was able to find out that particularly temperature has a lot of impact on rice production. When the temperature or the temperature is high, it affects the rice production. You know, when we're talking of modest land surface temperature, we talk of night and day, but when there's high night temperature, the production, the yield of rice reduced. So those things work hand in hand, even the same with solar radiation. So you find out that all these things which are already in satellite, we can use it to know the pattern of yield over the years and know why the pattern is so. We'll now check the climate, the temperature, the solar radiation, use it to model the rice. We'll now know, okay, from the year 2000 to 2010, these are the pattern of the temperature and these are the pattern of the yield. And to give us an insight of what is happening in the climate, or what is happening in our system, what is happening in the environment. And it will help us to know how to mitigate those things and give us a very sound recommendation for the government or for any other person or the farmers that will make use of it. Thank you.
Okay,
Yes.
Thank you very much, Izzy, for the very fruitful sharing. And we can see that both findings, both research is very awesome. That can be applied by the researchers, decision makers, and planners in order to provide the sustainable agriculture and to enhance economic of the community as well. So I'm afraid that all the time we have for today. So finally, we come to the end part of our webinar. We would like to say thanks again to the panel speakers, Dr. Izzy and also Dr. Ferd, for making your time and being here to present a very informative and interesting talk. So we hope that it's not going to be the last and first and the last, and hopefully that we could go to your place or you come to our place.
Yeah, Dr. Practice, yeah. Of the collaboration, yeah.
Yes, okay. Hopefully
Yeah.
that this pandemic era will end soon. Okay,
Yeah.
so hopefully that this webinar will be beneficial for everybody, especially UMK, Malaysia, and also Nigeria, and we could collaborate in the future. And see you again. Thank you everyone, to all the audience and viewers. Hopefully that we could see each other again. Assalamualaikum and very good afternoon. Thank you very much. Okay, easy, Dr. Ferd.
Thank you,
Okay.
Amal. Thank you.
Okay, thank you.
Thank you, Dr. Fad.
Thank you, Dr. Izzy. Nice to meet you as well.
My pleasure.
Mm.